Good everybody, welcome back to another video. So today we're going to talk about C pointers, and I'm just going to give a brief crash course on it, mainly because pointers are probably the most important thing you see. So let's just get started with basic pointers. So what is a pointer? Well, first let's just see that this is a variable. So this variable x is of type int, and then it is set to 5. Now this is a pointer. This means that this is a pointer to an int, and in this case, what are we pointing to? X. And all pointer is just a memory address. And you'll see why throughout this video that this concept is very powerful. But first, let's just debug it and see what is going on, because that's kind of the best way to learn. Alright, so we're in this debugging view right here, and we've seen that this pointer is about to get declared. When we step forward, this pointer is declared, and then you can see down here, this pointer has a memory address, but the contents of that memory address point to x, which is 5. Now, this is a dereferencing operator. So when you do star pointer, you're saying, I'm not changing what pointer is, because keep in mind, pointer is this gigantic memory address number. I'm saying that we go to whatever the pointer is pointing to, then change that value to be 6 in this case. So in this case, when we step through, you'll notice that x actually becomes 6 down here. And we can also see this in the virtual memory view by just pressing and x, and then that'll point you to the memory address. So now you can see these 4 bytes, since ints are 4 bytes. And by the way, it's little endian since we are in an x86 machine, but now x has changed to 6. So very easy to understand what a basic pointer is. You're just pointing at something through a memory address. But pointers obviously are very more versatile and complex than just what we've shown here, because otherwise they're kind of boring. We can also see that arrays are pointers as well. So this time we're going to define an array of 12 characters. We're just going to call it a string because that's what it is, an array of characters. And we are going to set the 5th element of this array to be @ symbol. And this is pretty much a normal declaration, and you can just do a assignment here just like so. That's just assigning the array. But all I'm trying to show here is that this is actually equivalent to this, because arrays, again, are pointers. And to prove that, when we press the ampersand symbol, we can go to that array, and this is the array. And you kind of see the ASCII here. The @ symbol changed, again, the 5th position of this array. Now we can actually do arithmetic on this pointer and change the 5th element to an underscore. And it's the exact same thing as this. We're going to get the pointer. So this is pointing to the 1st element of the array. Then we say we add 5. So what's str here? Str is this BF958 address. This is BF958. We add 5. When you look at that, it's the exact same position. When we step through it, it gets modified to a underscore. So it's the exact same thing as if you were to do it with the brackets. And in fact, I believe the brackets actually just become this after in the compilation process. Now we're going to talk about structs. So structs are kind of C's way of defining classes and objects, but they're more simple than the OOP version of objects and classes. So there's nothing like private modifiers. There's nothing like inheritance. All a struct is just a collection of bytes that you decide to be something. And that's very crucial, because when we define the struct here, for example, I've defined this date struct called Christmas, and that is, of course, the month is 12, day 25, year 2024. When we step through it, we have this struct variable right here. But if we go to the actual location of it, again, just type ampersand for address, and then you type the variable name. So this is actually Christmas right here. So these 4 bytes, the CPU knows nothing what this is. This is just 4 bytes inside memory. But the struct just says, to us humans, we can kind of do stuff like, for example, accessing structs. If I scroll up here, for example, we can get the year. We can do a dot notation. I'll show the difference of the arrow and dot notation later. But all that is saying is that we've interpreted this 4 bytes to mean something more special than just random numbers. That's what a struct is. Now, just like up here where we can assign arrays as pointers and even just random primitive values as pointers, structs can also have their own pointers. That's what this is. So this Christmas pointer right here, it's just going to point to the struct. So it's the exact same thing. It's saving the memory address of these 4 bytes into this value, which is corresponding down here. And then it's just going to set it to that, and then whatever you do to it, it will do to this Christmas struct. Now, let's actually play with this a little bit by looking at two types of function calls in C. And this kind of goes back to the previous video on x86 stacks. And this basically says, first, we're going to look at how to pass by reference. So pass by reference means we're only copying the pointer, and that's very fast because a pointer is just a constant value. So let's step into this. We're going to be up here now. Notice that our local variable, which shows the stuff inside our current stack frame, is just a pointer. And that means that this function scope only has one pointer to the struct. So when we do something, let's say now we're going to go back in time, look at 1584's Christmas. So we step through it. Now, notice that this didn't change. The date didn't change, or at least the date pointer didn't change. The actual date did change, because if you notice, the year changed to 1584, but the location of the memory never changed. And that's why we notice that we have this arrow notation. This is just saying I'm pointing to this, and then I'm changing whatever I'm pointing to 1584. Date never changes, and only year changes in the original struct. So notice that this becomes changed, and Visual Studio notes that by updating it in red. Now we're going to just step out of it and go back and see what the difference this compared to pass by value. So pass by value copies the entire thing. So let's just step forward. We're going to step into this. Now notice that we're passing this entire date struct in. So if you notice the locals tab, so again, this locals tab shows you what's inside the stack frame. When we step forward, this date changes, but there's no memory address associated. Notice how everything's red. Everything changes. If we go to, so before I go to this variable address here, notice this is our original Christmas pointer location. Now I'm going to do date. Notice this is F984. If I go here, now it's a completely different thing. It copied everything to a new location, and then it set everything that way. So that just indicates that pass by value needs to do a deep copy of everything, puts it into the stack frame, and then it becomes a new local variable. But then, just like that, we need to also return this new local variable, because it created this new local variable, but if you don't return it, then it just gets destroyed with the stack frame. And by the way, you can see the stack frame up here. So that's why when we press enter, we'll return back. And this time we will be back. And if we go to that address again, so and date, you'll see unable to evaluate expression because it's gone. The stack frame is gone. However, if we go back to Christmas, it's still here. And this didn't get changed. We had to reassign it back in order for it to change. So yeah, that's the difference between pass by reference and pass by value. The last thing we're going to talk about is probably the most complicated of pointers, but it's a function pointer. So just like how you can point to a struct, you can point to an array, you can point to an int, you can point to a function as well. And this actually has some pretty dramatic consequences, especially when you get into operating systems programming. So this function pointer is actually an array, but we're going to see what this says in a moment. First, we're just going to look at these two basic functions. So one is just adding two numbers, one is just subtracting two numbers. They both return an integer, they both take in two integers. So nothing too complicated or exciting here. What this says is I'm going to define an array that is filled with pointers to a function. Because you can't really put a function inside an array because the function is just code. But what you can do is you can point to the function, because keep in mind, all that function is just assembly code. Remember labels in the previous episodes? That's exactly what a function is. So for example, this add function, if we go to disassembly, and if we just scroll up a bit, up here, I think, yeah. So this is just the add function right here. We have this move, push, subtraction, setting up the stack frame, and then I can't read a bit of these because there's also some security things that it sets up. But then at the end, it returns, and then, yeah, so all of these are functions. So for example, this right here is the function address for add. And what we've just put in this array is just that function address. Of course, now it's just a pointer. And in this function pointer array here, we can kind of toggle between both functions. So I set int11 to be function pointer array at index 0, and then I pass in the parameters int for both, and then it returns the int as well. And this is 5 and 6, so that's why it's 11, because it's selected by itself at runtime what function to use. And that's actually very important consequence. So let's just step down here and run it as well. So 11 at the end will be, of course, the number 11. That is because it selected the function at runtime. You might ask, this might be a very weird and complicated use case. Is there any real use case of this? And the answer is yes, because functional programming always, well, not always, but a lot of times uses stuff that variables equals functions, and then you can call it. You can do lambda functions this way. You can also even do callbacks. So events are implemented this way because, for example, if add and subtract are callbacks, say this will be like, if something happens to this array, please call this function add right here. And then this calls it here during runtime, and then it goes back to your custom made function. So I can change add to be a callback. So this could be a callback. Now you can kind of see why pointers, especially function pointers, are very useful, and why C is pretty much what they call the language of pointers. So hopefully you enjoyed this video. In the next video, we're going to talk about dynamic memory allocation, so even more advanced C features. And yeah, so stay tuned until the next one.